the way we're going to do this is first they're going to have an opening statement for about 4 or 5 minutes. Then I'll ask some questions, and then you're going to ask some questions. So think of good questions. So the first panelist is Alex Lupsasca, and he's from he's a professor of theoretical physics at Vanderbilt, and he's also a research scientist at OpenAI. And Alex can give us insight from both academia and from OpenAI. Then the next panelist is Kyle Cranmer, and he's a professor of physics at the University of Wisconsin at Madison, and he's director of the Data Science Institute and one of the leading experts on applying AI to physics. And in fact, we heard in Lance's talk some recent work he's been doing on theoretical physics. The next panelist is Eva Silverstein, and she's a professor of theoretical physics at Stanford, and she's widely known for her work on string theory and cosmology, and more recently she has been spending time on applying physics ideas to improving machine learning, and I hope we're going to learn a little bit from her about that. And then finally, from the Supercomputer Center, we have Wahid Bhimji, and he has a PhD in high-energy particle physics. He's Division Deputy for AI and Science at the National Supercomputer Center at Berkeley, and I hope he's going to tell us a little bit about plans for, that the National Supercomputer Centers have. So my first question for the panel is about how AI can help us in a non-trivial way. So I'm old enough to remember a different revolution. Maybe many of you are too young to know that this actually happened, but computer algebra was a revolution in theoretical physics. Today, everybody, 90%, more than 90% penetration uses computer algebra as a way of communicating, a way of just doing their physics. And one of the things that computer algebra did is change the way that we do physics in a very basic way. So one idea that we saw this in a little bit in Lance's talk is that not only could we go faster on the old ways of doing things, but there are new ways of doing things, specifically guessing. You make a large guess, and then you use the computer algebra to try to verify the guess. And that's like a revolutionary idea, and it touched many aspects of in physics. So my question to the panel, and we can start with Alex, is what are the new ways that we can see that AI can really help us, different ways of thinking about old problems?
Yeah, I think in the last year, the capabilities of the models have dramatically improved. So I'm an academic. I never thought I would be at an AI lab. In fact, a year ago, I was a bit of an AI skeptic because I tried the best models at the time, and they weren't really helpful in my work. But I kept hearing that some people were finding success with them, and I kept trying them. And when the reasoning models came out, and I finally got a chance to apply them to real problems, they started to really impress me. And then GPT-5 came and did something that I thought was really amazing, and I just kept being surprised. And at some point, they got so good and did such impressive things that I thought, okay, I gotta switch my research direction and start using them all the time, and end up at OpenAI because I think there's huge potential for accelerating science. And now I use these models all the time to do physics research. And there's at least two ways in which they've changed my workflow, which I think is what you're getting at. So one way is that when you do research, certainly in my field of physics, but I think it's true for everybody in this room, you spend a lot of time being confused. You ask a question, you try to answer it, you get some partial answer. How does it mesh with this other thing that you know? This seems inconsistent. You bang your head against the wall, you run into an obstacle. I would say my experience in the last few months using GPT to do research is that the amount of time that I spend being confused has dramatically dropped down, which feels like a superpower. I haven't gotten smarter, but I do a calculation. I think, what does this mean? Wait, how does it mesh with this other thing? I just asked ChatGPT, and it says, oh, of course, it's because you're not quite thinking about this correctly, and it connects to this other thing, and if you view it this way, I'm like, oh, okay, of course. So Just using it a lot, I'm less confused, and that makes me happier, and I move faster. So that's great. And I think another way in which it really changes the way you work is that it takes a lot of effort to explore an avenue of research, and typically you think really hard about how am I going to tackle this problem? I'm here, I want to get here. What's the route? And you don't have that much time or energy really, and so you want to plot your course carefully. But the great thing about GPT is that you could just say, here's an idea and push forward very fast. It may not get everything right, but it'll just signpost some milestones along a certain line of research. And that is so useful. And in fact, you don't have to do it in just one direction. You can just have 10 ideas and launch 10 scouts that push into different directions. And what's great about this is that it's very hard to be the first to push into the wilderness. But if you have some companion that's highlighting some signposts along the way, that gives you a huge help. So I think these are two very concrete ways in which AI has changed my workflow, and I think has made me faster and happier.
Does anyone want to add anything to that? Or we could go actually to the question I should have asked first. Give me your thoughts. You want to make an opening statement, which is really the right question to ask first. So,
yeah, okay.
Please go ahead.
So, I mean, I have, in some sense, a little bit of an unusual background because initially the first part of my career was an experimental particle physicist. And so that was like searching for the Higgs and setting up the statistical framework for that. I would say that I learned a lot about the social aspects of that. Trying to get 6,000 physicists to agree on how you're going to do something for the Higgs discovery was maybe the bigger achievement there. And I think it's worth keeping that in mind, that even if we have amazing technology now, how it plays out, like what Nathaniel showed, how that's going to play out is largely a social question too. After the Higgs, that was like 2012. That was right when deep learning first started to take off. I pivoted to thinking about AI for science broadly. And then there were several years where it was a lot of trying to think about graph neural networks and how can you incorporate domain knowledge into the different architectures, include PDE solvers inside of things that led to stuff like with numerical weather prediction you see now. And I just moved into a lot of exploratory work. And most recently, what's been useful for me and some of my talks is that to try to give a little bit of a taxonomy about what's going on. And usually that's not about is it generative AI or whatever. It's somehow what kinds of capabilities is it enabling? And that looks very different across different areas of AI for science. So in some cases, it's more about data analysis, where it's it's kind of function approximation, approximating things, statistical analysis. There's another bucket, though, that I talk about as kind of exploration with confirmation. And what's interesting is that applies to kind of molecules, materials, and mathematics. And they seem like at first they wouldn't have much to do with each other, but they're both huge design spaces that is very much what Sergey's point was at the beginning of kind of search mentality, or searching through a huge design space, and then you have some notion of confirmation. But one thing I thought I would call out there is that in the case of drug discovery and materials, it's not an exact mathematical statement. It's more that some property is verified, right? So, and maybe that's in a lab, so experimental data. In math, you have that actual lean type proof, and with the stuff with Lance, it's in that same thing. You're searching through a huge space, and then you have this set of linear equations to check. But there are other places where you see it in theoretical physics. Sometimes I call it the computational microscope. So for lattice QCD, you're trying to make a prediction. You know the theory, but it's a big numerical challenge of how do you actually do that. And that's where things like Markov chain Monte Carlo and things like that. And we're seeing AI and generative AI techniques leading to totally new classes of sampling algorithms that have different scaling behavior. So there's all sorts of different capabilities. But I think for a long time, I wasn't all that excited about language as a scientist. I was interested from the sidelines about what's going on with language modeling. But what's happened recently has been, I think, really impressive. I say one piece, a few years ago, I had Judeo Pearl, who's here, come to give it. We invited him for a session we were organizing. And I like the points a lot about causality and what you kind of was impossible even with an infinite amount of data, because you're just stuck to kind of correlations. But somehow I think that language is, exposes actual interventions and things. You have sentences that are telling you stories about what happened. And I think that somehow that's very important for being able to navigate through these spaces. So when you have that design space that's huge and you're trying to, the only way you're going to succeed is to do bias sampling over that. And what is your kind of prior thing that's biasing the sampling? If that is guided by kind of reasoning type things that have causal stories and a lot of historical examples, you can guide that in a way. And I think that that's somehow really magical, and well, not really magical, but it's amazing to see what's happening. And so when it comes to searching hypothesis space within within a particular framework like quantum field theory or formal mathematics, or designing new experiments that you're going to use to try to figure out like in Nathaniel's example and what was shown, like you have say maybe two different theories that describe that bump. Like, what do you do next? Like, the next thing of that conversation is, well, if this theory is true, then I should see this other signature, and so I should go look for that in the data, or I should build a new experiment that's going to see if that happens. And before, if you did that in a really brute force numerical way, you would have had no idea how to do it. But now that somehow seems very clear. So that's very exciting, I think.
Eva?
Great. Well, thanks to you and the organizers. This is really an incredible meeting. Let me cover a couple of things that I think are complementary to the beautiful talks and discussion we have so far on particle physics, amplitudes, and math. So one is theoretical cosmology, which is a beautiful subject that ranges from the observational frontier to the theoretical frontier, sort of hardcore quantum gravity to galaxy surveys and so on. And there's a grand challenge there to make use of all the information that in principle is in our patch of the universe, but that we can't get because we can't predict the weather. So if we can predict the weather, let's predict galaxy formation as well, down to sort of frontier quantum gravity. How does the space-time that we really see with positive cosmological constant and so on emerge from something tractable? And there's progress on that from HI, but also AI is really helping. So in our group, for example, we have needs for understanding and doing computations of quantum field theory, quantum fields in a space-time that has non-trivial topology, which plays an essential role. And recently, for example, one of the reasoning GPT models connected some problem of that sort of tracing CMB photons in a non-trivial topology to some hardcore, pretty sophisticated work in photonics. So these are two disparate areas. I would have had no clue about the photonics results had it not been for the AI. So brings things together. But now let me turn to the thing that we actually sort of advertise, which is that AI models themselves are an amazing physical system. So again, this is articulated beautifully in Nathaniel's talk, the difference between sort of reductionist and emergence. In condensed matter, we say more is different. And that certainly applies to AI with these emergent capabilities from simple building blocks that we can inspect without torturing animals, and so we can do the example of as in neuroscience. So this is not news, but there's a huge renaissance in this kind of work. I'm just going to share one fun example of this that we've been excited about recently, which is to do with the way physicists look at a problem in terms of symmetries. So the transformer models, which are at the heart of language modeling, although there's a big scaffold on top of that, evidently, have the property that they have a large group of continuous symmetries that don't affect the output at all. This is in the attention heads of the model. For those, probably everybody knows what that means. And so in physics, the first thing we do with the physical system is we understand its symmetry structure and the consequences of the symmetry, and also often what the consequences of breaking the symmetry are. So these continuous symmetries imply conserved currents in the learning dynamics, much like Nether's theorem in physics. But more interestingly to me, there's a motivation for breaking the symmetry, which just comes from the fact that there's all these extraneous directions that are carried along in the computations but are doing nothing for the model. If instead we put in an explicit breaking, so for example, the way we're doing it these days is to put in a hard, untrained bias. So there are weights and biases of neural networks. The biases, at least according to every open source model, are not being used in these transformers. So they're there to play with. You can take a hard, untrained bias with a little bit of stochasticity during training to fully break the rotational group. And the very fun thing is the model can now use that newly introduced special direction to its advantage. So it can then take classes of tokens or more general inputs from the residual stream, learn its key matrices to align useful classes of tokens with that bias vector and hence amplify the attention, or vice versa, it can anti-align them to suppress. And lo and behold, the models very much do this if you train them in this way. So they have well above chance they align. And furthermore, you can do a semantic analysis that you can recognize semantically what the classes of tokens are that are being enhanced and suppressed. And also at the baby level, I'm talking GPT-2, 124 million, nothing to write home about. But in that context, this is also predictive of improvements on logical reasoning, sort of baby logical reasoning. So I'm really excited to try this at higher scale. So that's, more is different. Another slogan is less is more. So toy models help. And I don't know how I'm doing time-wise, but there are examples of that as well, involving that people from NYU found this beautiful, parity task where they could see explicitly and analytically predict the evolution from a probability distribution that's calibrated to the sort of crappy pre-training data where there's, a mix of short and long, correct and incorrect chains of thought, to that evolving to when you do the RL that you should do to do reasoning, the probability distribution morphs into something that's peaked on long, correct chains of thought. And so it's you can understand that at the sort of toy model level. In fact, the example these guys in this paper give is you want, the models to dig out the Terry Tao chain of thought from Max Stack Exchange instead of whatever else. Okay, so okay, that's my spiel. Let me stop.
That was the token Terry joke.
Yeah. Liven up the audience there. All right, yeah, so I'm Wahid. Just to give a bit of background of my perspective here, as mentioned, I'm at NERSC, which is the DOE's mission supercomputing center for the open science part. So that means we support like a broad range, like particle physics, that's my background, but also material science, earth systems, etc. And we've kind of had AI deep learning projects at least for the last 10 years in all of these areas. So, for example, ForecastNet, which is one of the leading weather prediction models we developed with NVIDIA, for example. And so, like Kyle, I think I was initially interested in what kind of models we could use for science rather than language models. But I think more recently we've seen similar projects actually to what Nathaniel described, where we can maybe use AI agents alongside traditional simulations and so forth. So then, as well as that, I'm also involved in this Genesis project that many of you may have heard of, is the Department of Energy's new AI initiative. And I think what's exciting about that is, one, that we've always kind of wanted to build a productive platform for scientists to actually implement AI, and we've talked about that a lot in NERSC for the last many years, and now it's actually part of the Genesis mission, explicitly talks about building a platform that not only connects high-performance computing, but that also directly connects that with the DOE's data sets and experiment. And so I think that's another interesting direction to go in. But I think the good thing about Genesis as well is the sociological aspect that was made. It's actually really now a forcing function to get people together across national labs and also universities to try and push this forward. So that's kind of the background. My perspective on things generally is maybe, I have fortunate to go after all these talks. I think I really agree with what was said by Sergey, for example, that in sciences, there's things that we're interested in. First of all, I should say there's a base level 0 of productionizing what we already know is productive. And so I'm spending a lot of my time on that. Recently, it's not very exciting, but I think it is very important to do. So that's a base level. But really, to go beyond that, we kind of really need to look at out of distribution generalization and non-context learning potentially. And there, I think that makes it really exciting as a playground for AI in general, but also how do we actually achieve that within science? And I think there we can really benefit from what Nathaniel was talking about, that we have simulators, that we also have ways of interacting with experiments. And so in particle physics, that's often reanalyzing data that's already there. But in other areas, you can actually run experiments autonomously, etc. So I think that really gives us the opportunity to go beyond, in-domain learning. But to your point about what really can take us even further, I think is trying to connect all that in a way that actually has a feedback loop. So, we talk about differentiable simulations, but there's also reinforcement learning. But I think there's lots of other potential approaches to automizing that whole chain. And I think that's an area I'm interested in. I think, and this might be a little bit controversial, but I think we also maybe have to go a little bit beyond what we think of theory. So here you were talking about using tools such as Mathematica, and phenomenologists are always interested in what actually practically works. But there's probably no fundamental reason why the secrets of the universe have to be interpretable by humans. So ultimately, and AI might kind of take us there where we have things that practically work, but we don't actually know why. So that's controversial for a theoretical physics themed
It sounds like
workshop,
a very unhappy world. With this physics, I wouldn't be able to understand. Okay,
Yeah.
So maybe we can return. You have any more comments?
Yeah, I think this gathering is a great opportunity to take stock of where we are in the development of AI for math and theoretical physics. And we've already heard some talks that I think should change the audience's mind if they were not already converted to the revolution that's coming. And I have a bit of a provocative claim, which I think is true, but maybe it'll kick off some lively discussion, which is that I think this year is an inflection year for science. And I think that 2026 will be the year in which AI does to at least my corner of science what it did in 2025 to coding. And so let me make that very clear. At the start of 2025, if you were a software engineer and you were using AI agents to do most of your coding, you were an early adopter. And if you fast forward to the end of the year, not even 12 months later, by December 2025, I have a lot of friends who are coders. And if they're not using AI agents to write most of their code, they're in danger of being obsolete. Now, it's January, February 2026, and in just the last 3 weeks, we've put out 2 papers with colleagues in academia, Alfredo Guevara, who's here, a postdoc at IAS, David Skinner, a professor at Cambridge University, Andy Strominger, professor at Harvard, myself, and Kevin with OpenAI. We had what I think is a very solid physics result in the theory of gluons, where the final answer was absolutely uncovered and derived by ChatGPT. And just an hour ago, we posted a follow-up doing quantum gravity. It's the same calculation now, but with gravitons. And the pace at which the second paper came out is indicative of how accelerating AI is for science. And I think that if you're using these tools, like some people in this room are right now, you're an early pioneer. But as these capabilities continue to evolve, and we've also used some internal models, but very soon everybody in this room will be able to access this. I think if you're not using these tools, you're going to end up being at a disadvantage and maybe start being left behind. So this is kind of my provocative claim. I think we've reached a certain milestone, and it's a very exciting time to live through in science because I think we're going to see lots of things change.
Well, I can't resist the next question, which is, so AI will clearly help us on like medium level physics where more or less we know what we're doing. But there's, of course, the next class where it's like magicians are at work and they do work which is, you could say they have no right to do. It's like a bold leap of some kind. Or there's also work which could be extremely technical. We've heard that. So I guess the question is, what's your vision for AI helping us with that class of problems, the ones we're really interested in?
Well, okay, I was struck by a phrase that Nathaniel said in his talk, that something that used to take 30-something physicists years to do, now you can do overnight with an agent. That's an insane jump. I think you're asking a little...
Yes, a little different.
A little different, which is not just how fast we can do things, but the nature of the discoveries. Yes. And to this, I will say, I think complexity is in the eye of the beholder. So a year ago, I was using ChatGPT. It was great for email, but it wasn't great for solving PDEs. And then the reasoning models got really good, and all of a sudden you could solve PDEs, and that was really impressive. And then I wrote a paper in June where I found some new symmetries of black holes. That's a very hard calculation that I'm very proud of. And when GPT-5 came out, it could do that. It could rederive that within 30 minutes. And that's when I freaked out, and I thought, okay, like I gotta get ahead of this and figure out how to use this tool. And now I would say that we have models, for instance, the one that we used to help with these papers I just mentioned, that I think do things that I'm not capable of, or that would take me an extremely long time to do. So I think the edge of knowledge is very jagged. The human frontier has a certain jagged shape, and the AI frontier has a different shape. And there are areas where the edge of AI knowledge is now, I think, pushed beyond certainly my abilities. And I think it'll because this edge is so jagged and it grows fast, but it grows at different rates in different areas, it may be that, in your particular area, it hasn't gotten to that point yet. And we were talking at dinner last night with Terry, and I think he said that it hasn't met this threshold for him. So maybe it'll take longer to impress Terry. But certainly for me, it's happened already.
So Kyle definitely looks like he wants to say something.
There's lots to say. I mean, I think that trying to be specific about it. I mean, I think two things I'd say. One is this ability to connect different things that kind of we collectively know, but no person knows, and see those connections. You were talking about the photonics example and stuff that I've been doing with Lance. Like very quickly, it was like, oh, I had some idea about random linear algebra, and then it was like, oh, now there's this p-adic thing lifting the algorithms that I didn't know about, and there's software there. And then, oh, we're doing something now with like mixed integer linear programming and what the systems operations people do. Like it was like 5 different, very well developed fields that I'm not an expert in any of them. And within like a few days, I've implemented the same problem with like dramatically different computational and conceptual paradigms. And so I think that, I mean, I would count that as in that class, and the chance that doesn't lead to major breakthroughs, I think, is small. I mean, those kinds of connections are going to lead to big ideas, and so I think that that's kind of likely around the corner. There was the other one that I think is maybe interesting and is also kind of connected to a conversation last night that we were having was that so within math we were talking about, okay, you can prove all these things, but at some point it's almost like AI slop of mathematics is the worry that I have, that you just prove like billions of things and what's interesting, right? And so the conversation was like, okay, well now partially you can say here's a theorem, and you can start to look at what does it depend on? Can you think about different axiomatic structures? And that's where a lot of the really interesting stuff is. And I think in some sense, the idea that, okay, here's all of this tower of mathematics, and I want to like transition it to a different fundamental like axiomatic structure, that would have required so much work that you just never would have done it. Right? And I think similarly, if you wanted to go back and revisit, like in particle physics, like when every time you suggest a new theory, you're like, oh, I have to go check the flavor constraints, and I have to there's a whole tower of things that you have to satisfy, and it's so much work that you basically never undertake that. So if you get to a point where you can say like, oh, well, what if I change this fundamental assumption, and then in a somewhat automated way, you can think through all of the consequences of that and check to see whatever, you're going to be enabled to take these like bolder leaps that you would have never been able to do before. And so maybe humans are still sort of driving that a little bit, but very quickly, some agent could suggest that. But that will be enabled once you can think through like all of the consequences very quickly, and that seems like plausible.
Does anyone want to add anything to this?
Well, I think we all agree it's speeding things up. It's letting us try things that we would not otherwise try because it would take us forever to tell if it was useful, if we could do the calculation at all. I am fascinated by the question of what we can learn from what we understand and come to understand about how AI models work and how they're trained in this regard of whether or not we can learn from that, like how likely they are to generalize, way out of distribution, for lack of a better term. So this thing where the probability gets peaked on correct long chains of thought is great. Those involve, the proper, validation and test loss and so on. But what can we learn from that about how how close we are to, something that would surprise Terry or whatever? I don't know the answer, but I think it's a really interesting question.
Yeah, well, I was going to say almost exactly that. I don't know the answer, but I think it's a question. Like even way back when we were using like generative deep learning to replace a physics-based simulation, there's this question of like, oh, but it's not physics-based, so how can it go out of distribution? And there's various papers that kind of addressed, oh, okay, well, you can amplify this much or sample or what have you, but I never got really a satisfactory answer to that. And now, again, like with language, we don't really know, are humans going really out of distribution or are they not? And if they are, can the current models we have not? So that seems to me a key question that AI researchers should be trying to answer. But then more to the point of how we can practically do it, I think, again, I would come back to we have this huge array of scientific tools. And so now really what we want to is enable this kind of scientific, not necessarily AI tools, but and some of them may be like AI surrogates or what have you, but like scientific tool calling, and put that in the hands of the AI so it can really like steer the useful instead of AI slop. It can produce like actual things we're interested in.
Thank you. So while I've got you, you mentioned a little bit about what the National Supercomputers Centers are doing. So the question is, what would you like to see them do?
Okay. Yeah, well, so obviously the one answer I'm going to give, I maybe didn't introduce, obviously the main thing we do at NERSC is provide big supercomputing resources. So, I mean, we have a current system with 7,000 NVIDIA A100s, which were at 2020 was a big resource. Obviously now it's blown away by other things, but we're putting a new system at the end of this year. And, most of that time goes, is given out by the science program offices, but we do have a small core where we have AI for science, like projects that can directly apply. But what's sad to see there, I think, in a way, is how oversubscribed that resource is and how even people from like MIT or Berkeley don't have access to even a small amount of compute for the kind of AI experiments they want to run. So, I mean, that's obviously something that I think about is like, not necessarily building more supercomputing centers, but broadening access to those or like putting it in other people's hands. And similarly to on the concept of broadening access, actually, I mean, I think Genesis is great, as I mentioned, as a way of like bringing together the community. And I also think it's great that there's this kind of building an infrastructure kind of platform coordination part. But I think there also needs to be a part, and I think that's going to come out. They're going to put some calls out now for other proposals. But I think it's really important that, again, there's a breadth of ideas there that go maybe beyond like kind of just applying current approaches and really kind of explore the space a little bit more. And then maybe the last thing I'd add is, which is actually related to maybe the tool calling, et cetera, or doing useful things is like the importance of benchmarks and evaluations. So that's something else that we're, trying to build in Genesis, at least a platform where people can put like benchmarks related to these grand challenges that they have. But there's loads of benchmarks out there, so there should really be a portal where all of these benchmarks can live, and particularly in areas where there isn't like as easy to have like theorem proving verification. In physics, it ranges from where you might need actual experimental data to verify, etc. So we can really put it there. And I also think people should be thinking of that from the outset when they do a new analysis or something. And I think you've talked about this before. Actually, is just actually also making it evaluatable. And now with the interpretability of like the ability of AI models to interpret, that doesn't need to be more than a description basically of the task and the thing, and the data set.
Okay, since Eva's sitting next to you, I can't resist the question for Eva. So suppose I'm a theoretical physicist and I have my toolbox and I want to help with AI. What do you recommend the direction? Like a good direction for...
Well, I just gave one small direction among many. I think there's a great interest in understanding the effect of the structure of data on what the AIs are learning. So there's an opportunity to use physics data. We heard a little bit about that already today, I think. But doing a kind of statistical physics style analysis of how you want to distribute lengths of chains of thought in RL and as a function of other things. There's the famous scaling laws, and there's a lot of subtleties with that. A lot really having to do with again with data, like whether or not it descends from some power law in the data. People are finding no, you don't need a power law in the data for those scaling laws to happen. So it's a very physicsy thing. What is where is it really coming from? Is it really reliable? Is it really optimal? So yeah, there's another thing I like to think about is sort of what I call pre-pruning, where the brain prunes at night if you do go to sleep. There's a notion in ML of recognizing sort of after the fact which weights really mattered, and then you can kind of distill away the ones that didn't really matter in the end, but doing that in advance in a principled way. So we have some mathematical ideas to actually use sort of the Abel-Jacobi map to try and, as an activation, to try and make progress on that. There's, it's sort of like any field, any sort of healthy, active field of physics. If you grab onto one part of it, you'll connect everything else. So all these aspects of the problem are related to each other and connected to each other nonlinearly. So I'm not saying it almost doesn't matter where you start. You can just get going and you'll find lots of excellent problems, and you can do experiments and,
Can I chime in
Sure,
one thing?
please.
So Lena Zidabrova, who's been here a few times, a well-known statistical physicist, thinks a lot about physics for AI. She has nice talks where she talks about there are a few major ingredients in terms of understanding the theory. There's like the loss landscape that you get, which is has to do with the model and the data that you have, and then there are the optimization algorithms that you use and their properties, and those are very important for a lot of the generalization that you have in the end, which might not be obvious. I think a lot of times physicists think whatever you optimize it, you get to the solution, but it's not. It's much more complicated than that. And there are groups of people that have been able to show all sorts of cool things that for certain kinds of models, especially the over-parameterized ones, that certain optimizers have dynamics that take you preferentially to some zero-loss solution that generalizes well, while others don't, and things like that. But those are usually very kind of special examples. But the one thing about it is that the framing of it is a historical one in terms of the optimizer. If you choose a different architecture, it might even be the same class of functions, but you parameterize it differently, the optimizer will see it differently. It's like a different set of coordinates. And so the same model's there, but where it takes you to in the loss landscapes will be different. So there's a coupling between all of these, and it's somehow the wrong it's the wrong, not the invariant sets of things to be talking about. There's some property that's invariant about generalization that's a mixture of the optimizer, the parameterization of the architecture and the data. And I've never seen anyone be able to characterize that in a way that's somehow invariant to reparameterizing the architectures and things like that. And those kinds of things, I think, is a very physicsy approach. And, I think people talk about it a little bit, but not as much as.
Well, I can't resist adding very quickly. I mean, the thing I've spent the most time working on in AI, physics for AI, is an optimization sampling scheme based on energy-conserving Hamiltonian dynamics with Bruno De Luca and others. And this is more predictive. You can take a Hamiltonian that will concentrate the results closer and closer to the bottom of the loss if that's where you want to go, or sample better than traditional Hamiltonian Monte Carlo. We have a microcanonical version. And so very much like what Kyle is talking about, there are principled ways you can use, in that case, essentially the Liouville measure on phase space. Integrate out the momentum, you get a Liouville measure on parameter space. And this is being useful in precision science. People do sort of field level inference with this. And I'm not sure it matters for training sort of industry ML models, because maybe you care about getting a good answer, but it doesn't have to be the very most precise one. But this is something that I think is open to consider.
Just one more, and then I'll have one last question before the audience.
I think there's an irresistible lure to physicists to try to understand how the models work, and that's a very interesting, worthy goal. But I also want to emphasize, I think there's a new, really exciting direction if you're a physicist today, which is to figure out a new workflow, which is how do you use these amazing models that keep getting better and better to make physics discoveries. And as we heard in Nathaniel's talk, you said multiple times that there is not enough manpower to resolve all the questions and problems that you posed. And I think we want to see more physicists adopt these tools and make more discoveries. That is the goal of OpenAI for Science. We're writing some papers now. We're trying to figure out how to do this, but we want everyone else to also help us do this and have their own discoveries. And I think that's how we're really going to use AI to make a big impact in the world in a way that people really feel in their lives. And I think AI is basically this amazing new scientific instrument. That's how I view it now. It's like a collider or a microscope, or it's basically, and it's a tool, a scientific instrument that applies not just to physics, but also to other fields and soon experimental sciences. And I encourage everybody here to use it as such and try to push the frontier of physics and science more generally.
Okay, so I have been encouraged. Yeah. But then I want to ask you the next question. Which tools should I start working on or start using? So, of course, we can all download ChatGPT Pro.
You're not allowed to suggest that you open AI.
Well, but what are the right kinds of tools?
Second tool you would do.
A little more specific. Give us a little more details. And you have under 5 minutes to do that.
Well, okay. First of all, I use multiple models from different competitors. I think it's good to have different ideas and different models. I will say in my experience for the stuff I care about, I have found GPT Pro to be the best, most useful tool. And I've tried the other available models as well. And okay, now I'm at OpenAI, so it sounds like I'm shilling, but I'm not saying that because I'm at OpenAI. It's because GPT Pro is the best at what I care about. That I went to OpenAI. It's the causal errors reversed.
I meant beyond. Okay, we can all download and buy.
There's two tools.
Beyond that,
there's sort of two ways to use the tools, in my experience. So one is the web interface, where when you work on theoretical physics and you have some calculations, some partial differential equations, something to solve that you want to think through, the way that I would go to my colleague's office and have a discussion and write some equations on the board, you can do all of that with chat. And I started to do that during the last year, and it was a little bit addictive because chat is always available, super fast, infinitely patient, has encyclopedic knowledge. It has some weaknesses, but it has all these advantages.
Great ideas all the time.
Yeah. Also. And I think for the kind of stuff that I do, this mode of working is just fine. But of course, there are other modes of working. So a lot of my colleagues that I talk to now, especially in the last month or two, I'm getting lots of inbounds from lots of colleagues at various places saying, oh my God, these new capabilities have totally changed the way I work. And I always ask them, what do you do? So there's a lot of people that use Codex, which is OpenAI's version of an agent that you can run locally on your computer. It'll make calls to an API, but it can access your files. It can read data. It can write codes to run a statistical analysis. A lot of the things that you would normally do as a data scientist, for instance, analyzing astrophysical observations, all that stuff, it can now do for you. And you can actually, I've seen people now that run like 4 agents in parallel, and they have basically like a virtual team of scientists doing everything. Yeah. So I think those are the kind of the two broad categories that I've seen using the web interface, which is the chat box, which is useful for some kinds of work where you're dealing with equations and things that you could talk about or work at the blackboard, and then the agentic coding when you're trying to handle large volumes of data. And I know this is something that you might want to use for your 50 megabyte data files filled with numbers and equations.
The one thing that maybe you can comment on it, or maybe others as well, is the hallucinations, the errors. So you can get a result, and then it takes quite an effort to actually, verify the app. So tell me, tools for doing that.
Yeah, I should say that...
Lean for physics.
Lean for physics. I think that actually, in the long run, might be part of the answer, and we're certainly looking into that. But that's not here yet. I will say, a year ago, when I was using ChatGPT 03, which was one of the early reasoning models that I thought was really useful for calculations, it would make typos. It would introduce mistakes in algebra and doing symbolic manipulations. That was a little bit annoying because you had to basically double check everything. I have found, I don't know, like in December, I spent a lot of time during winter break using GPT on some black hole symmetry problem. And I found that actually it was just doing really complex math without errors. I just kind of stopped checking at some point because it kept being correct. So I think, first of all, the hallucination rate has gone down. Now, there is, related to this, it's true there's a lot of unevenness depending on what type of model you use and how much compute it's given. So if, sometimes people say, oh, well, I went on ChatGPT, and they use the free instant version that responds in 5 seconds. And they said, I gave it this equation and it didn't solve it correctly. Okay, well, that's not the best tool, but we have much better tools that are available, like the extended thinking models that reason much harder and they check themselves. And a lot of the development that's going on is making the models actually check their own work. And we have lots of, proprietary technologies, different scaffoldings that, there are tools where if you want the answer to be really correct, you can make sure that it checks itself enough that
I assume these things will be available in, let's say, a year or now, or.
Well, GPT Pro actually already does this in some primitive, very effective way, but you can do a lot more. And I think in the coming months. Okay, I don't know.
Yeah, I think
Yeah,
again
actually
it
should
comes down to scientific tool calling because I have like Codex with the GPT Enterprise subscription, and it totally changes your life now for coding tasks, because if it does hallucinate and make a mistake, it then just corrects itself and does something different, and it's like busy going away, and eventually it comes maybe not to the most beautiful solution, but it comes to a solution. Now I think for science, all we need is some skills and tools that it can call that do what you want, what you need to convince itself it's not hallucinating, or what it needs to convince itself it's not hallucinating.
That's a great tip. If you ask a question, you say use SymPy, symbolic Python, which is a package, to check your answers. It'll actually write code and show you the code and run it. That's very useful. It gives you confidence.
If I can kind of like maybe meta instead of like specific tools in that sense, I think to me in my playing around, I played with a few of these things, a lot with Cloud Code and et cetera, but this idea that one of them was that you have, there's the idea of specifying what's your problem, right? What are the tests going to be? So like the importance of tests becomes more and more important. And then the other part was this idea that you're going to have maybe different personalities for different kinds of roles, and that you're imagining a kind of a team with different agents doing different things, and you can say one can be really pedantic and one can be whatever, and you have them. It started making me kind of reflect on how I organize my group, and a lot of these things have nothing to do with No, but honestly, I mean, a lot of the lessons learned are true of people as well. Like, it would probably help if I was just really clear about the specifications, and this is your roles and responsibilities, and it's right,
Do you have it unionized?
Yeah, exactly. They're asking for higher subscription fees now. No, but I think that in some sense there's a set of tools and things to be learned that are at that level, which are not like which tool do you like, but like kind of principles, design principles. And I'm kind of excited about the idea of like, different versions of there's, me instead of having a graduate student having this, but I like maybe better there's me and a graduate student that's also using it, or me and a graduate student and a postdoc and another agent, especially for bigger groups where not everyone can join. If you have an AI team member that joins every meeting, and then you want to come back and you're like, what was discussed? Catch me up. Oh, did they try this or X, Y, and Z? Or based on the current conversation, can you double check X, Y, and Z? You can have that, and that would have previously been very difficult for team science. I think that's going to be really exciting. And then something that Wahid mentioned a little bit, which I think is interesting, is like, how are we going to approach reproducibility? It used to be reproducibility was like the method section of a paper that was narratively written about you put the pipettes in here and you do this, and this is how you reproduce the experiment. Then we moved kind of towards like computational reproducibility, which in some sense is like, bit level reproducibility, but it lacks the semantics. It's just some Docker container that you rerun, and that's not all that interesting. But to be able to get back to a point which is basically narrative in nature again, like this is what we're trying to do, these are the steps, these are the tests you should do, the specification, and something that works for all the different AI models, and that you can rerun that whole thing again in a year from now when they're better models, is going to be interesting. So what's the new paradigm for reproducibility is kind of interesting.
So one comment from Eva, and then we're going to go to the audience.
Sorry, I'll be quick, but that was a great comment. I just wanted to say, and this may be very lowbrow, and I may be behind right now because of all the agentic progress being made, but just having something take care of the context window, because when you use these chatbots and you just abuse that and you're too lazy to start a new chat or whatever, it quickly degrades, and it is, but there's got to be a way for it internally to figure that out. And agents start with a fresh context, so that's, I think, one of the reasons that they're helpful, just that. But tools that more automatically take care of when you should really just refresh would be helpful.
Anyway, this was very insightful, and thank you. But now let's get questions from the audience. There. Yes.
Yeah. My question is about the non-deterministic part of the AI because of the autoregressive nature of it. I am one of those programmers who extensively use the vibe coding. So what I previously did 6 months, I can do it in an hour. So, but what I find is that depending on which model I use or where I start, I get different functions because of its non-deterministic. They're still functional, but it a lot of difference between that. But when you are doing the theoretical physics calculation, do you get the same equations all the time?
Yeah, that's a very good point. It connects to a lot of stuff that's been brought up, actually. It is true that when you ask an LLM a question, you get a probability distribution over possible answers. I think a feature of this that is underappreciated is that it's hard for us to actually know what the edge of capabilities of our models is, because there are probably lots of problems whose answer is within the distribution of potential outputs from the LLMs, but the pass rate, the probability that you get the correct answer is maybe below 1%. And you can't ask a human user, keep asking ChatGPT the same question 100 times and in expectation you'll get the answer correctly once, because then it's actually shifting the burden of work back to the human of like checking 100 answers. And so a lot of the focus in research within OpenAI for Science and trying to make our models better for scientific discovery is to use methods which are being developed that enable you to squeeze the probability distribution over possible answers onto the correct desirable answer. And there's lots of levers that are technical that we're not going to get into now, but we can talk about later over lunch, that enable you to do this. And I think it's probably always going to be inherently stochastic. You're not going to get 100% the same answer, perfect answer, but you can certainly, especially if you're willing to spend more compute, that's the brute force approach, you can basically force the answer to be overwhelmingly likely to be correct. And that's one of the tricks that we've been using in this business.
Does anyone else want to add something? Or next question then, over there.
Really great points, and I think we touched upon hallucinations. So let's say go down, let me think 5 years, 10 years in advance, where do we want to go? Ideally, as many of you mentioned, we want ideally an Einstein or a Riemann or somebody who would find fundamentally new. That's some of our hope. And the question is whether the current trajectory of LLMs, which is based on gradient descent, based on dopaminergic neurons in the brain, is that necessarily the method? Or will we need fundamentally different algorithms? And I might suggest, based on the research many people do in the science of learning in the brain, that the way we learn in any classroom is first we learn abstraction and then we solve problems. We don't solve 1,000 problems and then learn abstraction. And I think the reason probably is that the fundamental learning algorithm needs to be different, which is the one that's commonly used in the brain. Yeah. What do you think?
Maybe Kyle?
I mean, I don't know. I mean, I think that whether it's stochastic gradient descent or some search algorithm or whatever is in some sense like it's many layers deep in terms of the stack. I mean, there's different, certainly we're thinking about different approaches, but in practice, a lot of the success we see is not just, there's also like the human search over all of the different architectures and optimization algorithms and hardware things. So like the bigger search that's happening is not just within like, one search, like one, PyTorch, optimize thing like that. It's a social search that has a lot of different things. So, and especially when you get into various meta learning stuff. So I think it's hard to characterize what the algorithms are. Certainly there should be a layer which is of research, which is how can we improve at that level. I mean, I think in terms of getting to AI Einstein or something, that is it's a drastically higher level of strategies that you need to think about. I mean, one thing I would say a little bit, I don't know, is that while it's interesting and exciting to think about, can we like redo Einstein or refigure out quantum field theory or these kind of like things that we put at the like maybe pinnacle of human scientific achievements, or like could we go back to just train on the data before 2010 and then like rediscover general relativity? I mean, those are kind of interesting academic questions.
Yes.
I mean, that's what like Dimas Hassabis was saying is like, can you train did I say it the wrong way up until, whatever.
It's
and
okay.
then, yeah, I said it the wrong way. Oh yeah, sorry. Okay, whatever. You know what I mean, modulo something. But I think that there's a part where, okay, you could do it, but like what's the point? We already know quantum field theory works incredibly well. We already know like lots of axiomatic structures work really well. It would be nice to know, and maybe we'd feel proud of ourselves, but there's a bunch of stuff that we don't know how to analyze well as humans. And that's like, so when we talked about like a emergent phenomena at different scale, when the scales are widely separated and there's clearly like this phenomena happening at that scale, that phenomena happening at that scale, then we name the things there, we make an ontology, we describe the laws that describe how those things at that scale interact, and then we do it again at a different scale, and then we ideally try to connect those scales with some, some connection, and that's all great. But when the scales start to overlap and become muddy, it's very, very hard. That's like the strongly coupled type situations or something like that. And so when you think about like weather, like imagine I could do super duper fast weather forecasts at the level of like finite element analysis of things. What can I identify that hurricanes are things, or that like El Nino is a thing? You know, like a pattern or an emergent phenomena at a different scale, and get an AI to identify it, name it, and then try to describe effective laws at that scale that describe it, especially when they're not like nicely separated. Like there I see AI could do stuff that humans are really not very good at doing. And okay, sure, you could do the AI Einstein, but we kind of already doing pretty well with that. Like I think being able to say something interesting about really complicated phenomena like epidemics or weather and things like that is like, to me, a lot more exciting.
I was worried my claim was too provocative earlier, but since we're being asked about AI Einstein now, maybe I wasn't provocative enough. I think it's remarkable that this is what we're worried about in this room. But I think there are some things that are missing, and I'm going to give a plug to Kevin Wheel's public talk later this afternoon, because I think Kevin will address exactly what's missing when we have a feeling that there are some elements that are missing to produce a truly, that level of scientist with AI, and that's an active area of research.
Clifford?
Yeah, so in light of developments like the first proof challenge and even just like recent papers which are almost encroaching on expert domain, what's your take on what will happen when the machines are doing things that only a small number of experts can even evaluate as true? Like, is there a plan? Like, do those experts just use it and decide? Can you use reinforcement learning amongst those like 5 people who can tell the difference? Like,
How is it different from humans today?
It's not different. It's not different.
So
is the idea that they would just use the tool? Because the idea is like no one can judge except the
there are very few people that can understand our technical papers. So I think it's...
Can I just make a comment on that as a total non-expert, whatever, but just in response to my friend Cliff? I mean, I think it just reminds me of this statement that was made during Einstein's lifetime that only 2 people or so that understand relativity, right? But now pretty much everybody in this room understands relativity. Why? Because it's important, okay? So the thing is, I think, I don't see that that's a problem. I mean, if something is important, it will get verified, right? We decide whether we think it's important. If it's some really complicated technical result, maybe only a few people care.
Right, so the validation would happen just with individuals.
Well, there's also
It's a social thing. I'm saying
Social.
we have to decide what's important, and we verify the things that are important.
So can I make a comment on the social, unless you were going somewhere else?
No, go ahead.
I mean, this is a secondary thing, but one sort of pet idea I have is, can we use these models to overcome human foibles that come in the form of, things where groupthink, basically, the kind of situations where humans kind of collectively repeat the wrong answer to themselves and each other, over some period, and we all have our favorite examples of that. Those in my field know my favorite example of that. But I think it would be kind of fun to train these models specifically to look for what the mass of humans are getting wrong. And this includes, no offense to anyone, the biggest experts in some fields can be prone to this. We're social animals, even though we're mathematicians and physicists, even we are. And this is, it's really a side thing. Overall, there's enormous progress in the field, but I think it would be fun to sort of train specifically for that and see what comes out.
Yeah, I was thinking that earlier. You were probably talking about theoretic results such as supersymmetry, etc. But I was thinking in Nathaniel's talk earlier, like talking of that bump excess that was seen in Atlas and CMS, like who share a canteen. That's a little bit suspicious. And of course, before that, there was the pentaquark fiasco, where several experiments, found pentaquarks, which at the time didn't exist, but maybe since then do.
So of course,
Now, if AI is instead doing the analysis, maybe you can actually have actual blind analysis.
So, of course, there's a lot of historical data on physicists getting confused and wandering in random directions. So I assume that data can be used to train the models.
Of course, the models make up their own religions if they get together, so groupthink is...
I just don't think you want the machines to be too antisocial.
Andrew? Kevin, sorry.
I'm curious, and I'll direct this maybe at the 3 of you, and not an Alice, although I love you, Alice. How do you think about the role of documentation of scientific results when it comes in collaboration with AI? Because on the one hand, you don't document all the conversations you have with your collaborators. On the other, now you can. How important do you think that is?
Yeah, that's, I mean, one of the things that's most on my mind in my internal dialogue as I'm experimenting with this stuff. So you were talking about the context windows and things. I mean, a lot of the tools, they do remember things and they can go back, and there's a lot of engineering about when to compress them and all of this. But I would love to be able to do, have richer tools where I could do things like fork, go back to this point in the conversation and split, because it gets all polluted when you try to forget that, go back, because it has a hard time ignoring things. Yeah, well, yeah, so these kinds of forking things would be nice, and being able to do that in a more collaborative way would be useful. But I'm often, taking exchanges and basically copy pasting them into markdown files in my repos so that I can kind of keep track of how did this happen, because it's not necessarily easy to get to it from the, it's in the tool somewhere, but and sometimes I do things where I switch between different tools, I have to drive now, so I talk to ChatGPT in voice mode and reason about things, and then I get done, and I'm like, okay, write that up into a markdown, and then often I take that and I stick it into Claude Code and I do something, and then I'm using multiple tools and bouncing back, and it's not, the workflow is terrible. So it's a million times better than anything, last year, but it's still annoying. So I think it's a good question, and I'm thinking about it a lot, but I would love to see a solution that is thinking about teams and how team science works from the beginning. Yeah.
I mean, at the very least, we acknowledge the help it gave us, much like you would a human. I mean, you might have an embarrassing conversation at the board with another human, or now with an AI, where you don't really want to publish the entirety of that, and nor would anybody want to read it, right? But there should be a mechanism for I think I should just stop there. Yeah, I mean. By the way, Alex, I'm totally with you. I also do traditional physics with AI, but it so happens that in the ML publishing world, there's now a section where you must say what was your use of LLMs, and you do, and that's appropriate. I think we should do it also in in just all areas of science, because we are using them, and that's just an easy thing to do.
Yeah, I saw in my newsfeed, maybe it popped up, I haven't read it, but there was something about copyright for LLM written code, that recently there was a court case or something. Oh yeah, well, I'll have to read it afterwards, but it seems like now you maybe can't copyright code written by AI models. I'm not sure about that. But anyway, it links to a point really about we need a legal framework for that. We also need a kind of scientific framework for how we deal with this case where it's being authored by, potentially AI agents.
I mean, of course, you guys trained on data from all humans, and so
How do you actually do that?
that's acknowledged implicitly.
Acknowledge the internet.
Clifford.
Okay, well, first Sarah, and then Clifford. Go ahead. Yeah.
I guess my question was mostly inspired by Kiva, but coming up in general. So you made this, was that a question?
Go ahead.
You made this comment about the group think, and my first reaction was, I think an LLM wouldn't help us this, right? Because in some sense they're trained on group think.
That's exactly why I find it an interesting
Well, yes,
problem.
so this is my question, is to what extent, if we think about how advancing science, is it really we advance science by doing science faster with commercial tools, which I'm doing, it's amazing, versus are we needing to somehow develop more custom tools that kind of address, for example, this one issue of groupthink? And then just logistically, how do we do that? I mean, the amount of compute that OpenAI has is not what I have, for example. So how do we take advantage of what LLMs have given us, but maybe also finesse them to address some of these challenges that come up when you're practicing science?
Yeah, can I try to quickly say two things to that? One is it's not as bad as it was before the reasoning models, where before the reasoning models, the output was very calibrated to the internet. It was just a statistical imitation machine. Now the probability is morphed to really highly weight, again, long correct chains of thought, and we kind of understand how that works and how that happens. So it's not as bad as just being an imitation machine, even though it's not maybe totally deterministic. It's much closer. But as far as how to do this, I'm just kind of thinking aloud. Because of the first part of the answer, I think it's not there's no no-go based on, the fact that it's trained on the internet. But I think it would be just kind of fun to try to set up some pipeline to just try to deliberately attack this issue. Like maybe some of these examples we all have, like, there's the supersymmetry one, there's the one about like astro people debating whether gamma ray bursts were galactic or cosmological, and somehow I think the issue was that all the energy could be beamed in our direction, and that wasn't quite appreciated by the community. So maybe we could train it on historical examples where there's a huge swath of the wrong instinct. But I don't know, if other people are interested in this, I'd be happy to try to help like brainstorm how to do it, but if it, I don't know.
I mean, in some sense, code. I think there's a part where like every bug is, in some sense, a mistake, and you're like looking at how you recover from those things. Like in some sense, there's the correct code, but there's also, the success of the coding. Somehow, it's a different narrow example, but there is somehow like what were the corrective actions that needed to happen to recover from something, and I think there is lessons to be learned from there. It's not exactly the same, but it's.
Clifford would be last.
My first remark was on the sort of acknowledging aspect. That was more of a remark going back to what you were saying about the last revolution. We remember where people started using symbolic tools and what have you. And there was a moment where people were they put in their acknowledgements that some of the computations of this paper were first done by hand, but checked with computers. Very careful about trying to say that. So I'm curious to know what the analog of that is, but my main question, so ignore that because there's not enough time. My main question is a more serious one, which is, the other half of many of our jobs is that we are also training. We're also training the next generation of scientists. And that involves things like assessment and stuff. And I know we want to have a day where we don't think about those things, but they're clearly connected. If we're going to encourage our postdocs and graduate students to engage more and more with this kind of ways of doing science, we can't expect them to not use it for the other stuff, like exams and stuff like that. And I just have this big question for everyone, which is, what do you do? Because I'm not sure what I'm supposed to do anymore. So what kinds of things, what should we be training our students to be good at anymore? Because clearly it's not, just the sort of knowledge tick boxes that we had them trained on before. And then how do we assess that in the light of all of this? So I'm sure there's no single good answer. Just curious to know from the panelists how they think about this and what do they do.
I mean, that could be a whole week of. I'm not. It's a side, like two comments that sound like they're not answering it, but I think are relevant. One is think about tenure. This is not training. Right now, there's this situation that there are a lot of people that are the only people in the world that know how to do certain kinds of calculations, and they get jobs and they get tenure because they know how to do it, and it's recognized as important. And as soon as you have AI-type models that are basically going to automate those calculations, like those people probably are not going to be tenureable anymore. And like that's down the pipeline from the training part, but I think there's like a lesson to be learned from there, And then there was another comment I was going to make. This is gone, but I don't know. The other thing I wanted to say, which is for the work, do we have enough people? Like, where's the bottleneck and et cetera? One of the sad things that I realized when I was on this P5 panel was that we could probably effectively automate and streamline a lot of LHC data analysis. But if we start training a lot less people, like part of the value proposition of spending billions of dollars for the particle physics is that we're training a lot of people. And if we somehow undercut that thing and start doing it much more efficiently, then yes, we could, they're just not going to fund the big experiment and then it's dead. So there's all sorts of weird social things where there's a collapse mode that we should worry about, and also skill atrophy and all sorts of, and that's how all tied into the training question. I don't know the answer, but it's super complicated. Yeah.
Yeah, you're opening a whole can of worms, and we spent a lot of time thinking about this and worrying about this, as I'm sure everybody here is. Two quick remarks. One is, I think the kind of skill that is most sought after might change over time, and actually that might happen very quickly. So you mentioned that there are some people that have extreme technical capabilities, and maybe that will be relatively more commonplace now because you can get AI models to do very difficult calculations like we heard this morning. But I think if you're a professor and you're used to having students and postdocs that you advise, actually that skill is about to become even more valuable, because my experience talking with the AI models and using them in research is very similar to the way that I work with humans. When you have a student, you have to think about what problem to give them. It has to be interesting enough but doable. How much information you give when you give the problem, how you present it. It's kind of a skill to know how to pose the problem the right way with the right amount of information. And I think that skill carries over directly to using AI. And the people that are good at this are about to pick up AI superpowers. Now, that's great for the people that already are classically trained and have this experience. I worry a lot about the next generation, for sure. And I teach graduate general relativity. It's my favorite course to teach. And I always make the students compute the Einstein tensor for the general 4D spherically symmetric metric, and they hate me for it. But I did it too once. It's a horrible, brutal calculation. And of course, there are packages where you could just put in the metric and get the answer immediately. But I think it's really important that you do it once in your life, because otherwise you don't know what you're doing. You don't have to do it 10 times, but you have to do it once. And then you can go switch to doing it with the package. I don't know what the answer is going to be to resolve all these complicated questions with AI, but I think this is an element of it where we really have to insist that people know exactly what they're doing and do stuff at least once themselves. Well, okay, yeah.
Maybe you force them? Well, okay, this is not the right example, but generally I tell my graduate students not to use Mathematica in the beginning, right? First, they should do it by hand. Simpler case, and then they could switch. But it's up to us. We should, I assume in the future, the most successful academics will be those that properly train their graduate students. That natural selection hopefully takes care of this.
I mean, it is a weird situation where it's somehow an advantage to be old these days. It really is. I mean, but I find that the students who are really serious, and physics and math attracts these students, I find I don't have to do that much to get them to use these tools properly. Like, you can tell they're learning from them, but when they come and we have a group meeting or they come to my office, they're at the board, spelling it out. They're not like on their phone. So it's not as, I understand the concern, but I think people who are serious are doing their very best to learn, get it in their own heads. And of course, there's this history that people thought books were going to be the end of human intelligence because you wouldn't have to remember things anymore and, all that. So we can hope it's like that.
I just want to add that we've had a convening in the OpenAI forum that was it was focused on pedagogy in the era of AI. And I would be very happy to connect any of you with the faculty from all across the world that are grappling with that and creating frameworks and sharing their ideas and have been really successful. And I would love to connect you with them.
Yeah, one last quick thought, which is we should also be humble, because over a century ago, I think a physicist was a walking repository of Green's functions. To first approximation. And I don't know about you, but how many Green's functions do you know off the top of your head? Like 1, 2, And so the nature of what it means to be a competent physicist has completely, profoundly changed. And I think in the 20th century, we've seen it change faster and faster. And I think this is just the latest iteration of this. And Mathematica is a great example where, okay, in the 70s, if you could compute integrals off the top of your head really fast, like that made you a super-powered physicist. And then Mathematica came, and I think there was a lot of moral panic about physicists will know how to compute crazy integrals off the top of that. We're doing just fine. And actually, we're freed up to think about more important problems.
Sorry,
I say amen to that. But
could I very quickly respond? It's not that change that's happening. Everyone gets that. It's the pace of it and how we keep up with our mission as people who also train, who also must assess and say, out of this room of 100 people, this person, has this potential, this one maybe doesn't. How do we measure that? All of that's being blown apart in the space of months. And so that's what I'm getting at. It's not the fear of change. It's how we make sure that we don't blow up the models that, frankly, pay the rent.
Well, yeah, I'm not on the panel,
have another workshop.
I have great faith that the humans, we're intelligent enough to figure out a path. I don't know the answer or how this will work or anything like that, but I think of my colleagues, spectacular colleagues, and I think somehow we'll figure it out. Okay, I think people are hungry, so I've gotten hungry, and I noticed sandwiches out there, so just go and enjoy.